All right, hi. Welcome to Molecular Shapes. Again, this is only for honors. So if you're a general student watching this, feel free to, but note that this will not actually be on your test. Now, when we start examining molecules, their actual three-dimensional shape is very important. We need that to determine their function in life and really many other properties. For example, when you're looking at enzymes, I believe in biology, I haven't taught that in a while. These molecules, they're called substrates, I don't remember. They can only fit in certain molecules. They cannot just happen, to fit in some other enzyme. It will not work. So a theory that attempts to describe molecular shapes is called the VSEPR theory. I know that looks like VSEPR. For some reason, though, we call it VSEPR. VSEPR stands for valence shell electron pair repulsion. And it is a theory that points out that electron pairs will repulse each other. They will try to get as far away from each other as possible. So, for example, if you have two, kind of imagine this as balloons that you tied together. They'll end up, two of them will form like this. Three of them will kind of push at each other and form a little more triangle. Four will end up kind of three-dimensionalizing this and we get in this kind of weird shape. If you have some balloons with you, go try this. Blow up a few of them and try and hold them together, and notice they kind of push away from each other a little bit. So based on this, based on the fact that electrons repulse each other, we can compile a list of various shapes based on two main characteristics. The first being how many atoms are bonded to the central atom, and the second being how many lone pairs are on the central atom. This is a list of almost all the shapes we're going to have to know. Now, you get to know less of them, but let's look at some of these real quick. We have a shape that's called bent. Notice I have two atoms bonded to my central atom, which is red, and this represents a lone pair. Notice it's kind of bent. Or tetrahedral has four atoms bonded to the central. That's kind of how things end up working. So let me show you the ones that you actually need to know. All right, and here's a list of all the shapes that we will actually be talking about. I'm not sure why my PowerPoint didn't quite have the numbers typed over, but there are at least the numbers you can have. And what this says is if you have a molecule where there are two atoms bonded to the central atom, and that central atom has zero numbers of lone pairs, this is going to be linear. And linear, actually, you can see up here. So one atom, no lone pairs, two things bonded to it. Or let's say if we have 2 and 2, that's what we call bent. That says you've got two atoms bonded, and you end up having two lone pairs on the central atom. For example, that'd be up here. You've got two atoms, two things of lone pairs, and that's bent. You will notice there are more pictures here than what we've learned. I may cover this next year, but for this year, these are the only shapes that you need to care about using. But these are the shapes that we've got. So let's move on to practicing using them. We are now looking for the molecular shapes of each of these molecules. So to start with, we're going to draw the Lewis structures for these molecules and then label them. We're going to start by drawing a structure and then find our shape based off that. So CO2, we've got 4 plus 6 times 2 valence electrons. That gets us a total of 16. So we've got C, O, O. That'll be 2, 4, 6, 8, 10, 12, 14, 16. Now we are definitely short electrons. So I'm going to take 2 from over here, make a double bond, 2 from over here, and make a double bond. You could have actually taken another pair of electron here, made a triple bond, and left this a single, or vice versa. It doesn't matter because either way, we only have two atoms bonded to the central, 1, 2, and the central atom will not have any lone pairs. That is called linear. Again, two atoms, no lone pairs. Yes, there's lone pairs out here, but we don't care. We just care about the central. All right, so let's try CH4. I really wish I had a kind of erase all button. Unfortunately, I do not. Huh, my thing is not erasing at all. That's really weird. Alright, well, I found a way to erase it, so let's move on. CH4 is 4 plus 1 times 4, which is 8. So we have C, H, 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 and H. That leaves us with 4 atoms bonded to the lone pair, and 4 atoms bonded to the central, 0 lone pairs. We call this tetrahedral. There you go. We now move on to PCl5, which gives us 5 plus 7 times 5, which is 40. Now, you will probably notice this is a little bit unorthodox, that we have 5 of these. Meh, it happens. You basically just put all the atoms that you can have around it and just, well, make it work. Alright, I'm going to make a little bigger dot. Bigger. So, that's 10. We've got 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, and 40. And phosphorus not only has 8, but it has 10. It's like super full. It like went to a buffet and just kept eating, which, okay, really has nothing to do with chemistry, but whatever. So 5 with 5 atoms, 0 lone pairs, that is trigonal bipyramidal. Trigonal bipyramidal. Okay, I probably shouldn't have butchered that. Trigonal pyramidal. Yay. Woo. Alright, finally, SO3. That gets us 6 plus 18, well, 6 times 3. 24. So S, O, O, O gets us 2, 4, 6. And then we have 8, 10, 12, 14, 16, 18, 20, 22, 24. I'm going to erase that a little bit. 24. Please notice that I'm putting things in pairs. You want to do that as well. Don't just put single atoms by themselves. You will never have a single atom by itself in Lewis structures. So if you find that you did, sorry, but, well, you did it wrong. So fix it. Anyways, though, we're missing some electrons on sulfur. So I'm going to make a double bond. A fat double bond. Again, that could have gone here or here. It doesn't really matter. But that's sulfur. Now we have 1, 2, 3 atoms bonded to the central atom, and the central atom has no lone pairs. That is then trigonal planar. Woo. There you go. That's how you do molecular shapes. Feel free to rewatch, as always, as much as you wish. But that is how you do molecular shapes. I will not give you the chart on the test. Please know that. That's why, I don't know what I'm doing. That's why you've got just a few to memorize. So, have a good evening.